I'm just wondering, any of you bought a car recently? If you would have bought a new car, you can see anywhere from 80 to 100 million lines of code in the new cars. And 50 to 60% of that code is actually coming from open source. And some of you might have flown in from somewhere, right? The airline that you have used is actually heavily using open source. And the car rental, like you would have rented a car, even the car rental agency runs on open source as well. And simply put, let's say you have just Googled something today. You are the direct beneficiary of open source. So as you are looking at the open source, like there are multiple OSS stacks. So you may be wondering, who is taking care of the hardening and making sure that these OSS are ready for enterprise scale? So today's topic is all about that. I'm going to talk, how these open sources are actually designed and architected for performance and scale. Good morning, everyone. My name is Surya Dugirala. I'm the engineering guild leader for IBM Cloud. And I also had the opportunity, I have been working very closely with many of the cloud open source technologies. I'm the co-chair for Istio work group, and also I work very closely with Cloud Foundry community as well as the Kubernetes community, along with a few others. So I have three aspects of this whole thing, because I also happen to work closely with Fortune 500 companies. So I get three different points of view. Like from working with the enterprise customers, I get to see what kind of enterprise scale requirements these industries are putting. And working closely with open source, I get to see how these open source stacks are actually developed and architected. And being the engineering guild leader, I get to work with all the development teams within IBM Cloud when we bring these open source stacks and then implement an enterprise grade cloud platform. So when we talk about open source, right? Open source is like if you look at the 1998, actually the open source that we know of is born. So it's around 21 years old now. Right from the Linux to the Knative, or from Eclipse to the blockchain, right, Hyperledger. You see so many open source projects out there. One of the major things that open source is actually giving the power to all the developers. You need not be a developer in the Fortune 500 company, but you can be a freelance developer. You get exactly the same kind of power to make a difference in these cloud OSS. So when we talk about enterprise scale, right, all these different industries that I have personally worked on, and I would like to share some of my experiences. So when we talk about enterprise scale, let's take, for instance, a consumer appliance company. Let's say you have your washers and dryers and microwaves you're actually controlling through your mobile device. The amount of stress, the amount of the enterprise scale requirements that these APIs in the consumer appliance industry, if you look at one of the main company that I worked in this space, they have 2 million, they control 2 million of these appliances. 500 milliseconds or less is the IoT latency. That's what we expect from an end consumer. And then let's say you have a severe weather event. Last year when we had the severe hurricane, the amount of stress, the scalability requirements that were put on the weather APIs is humongous. Like for instance, we had to support 211 million video starts and 87,000 concurrent stream videos, right? So when you have this level of stress, like if you take, for instance, car rental. One of the major car rental that I have worked with, they are using some of the open source data stacks. They had to support almost 500 million data transactions per day. So if you look at across the industries, these kinds of enterprise scale that's actually put on these OSS stacks. So how are we actually designing these open source technologies to support these kinds of enterprise scale requirements? So today's talk, I'm going to talk about 4 things. The first one, if you just crack open a cloud platform, for instance, you will see multiple open source stacks in there. So we're going to talk about different layers of the cloud platform and what kind of open source projects are effectively being used. And then I'll go a little bit deep into a kube scheduler that I closely worked with our IBM research team to enhance the default Kubernetes scheduler to provide the enterprise scale ability for that. In fact, we have open sourced that last month. And then I'll go a little bit deep into the inner workings of an open source stack. For instance, because I'm the co-chair for Istio workgroup, I'm going to share some of my experiences working closely with the Istio open service mesh development. And then lastly, we're going to talk about these multiple open source stacks. Sometimes they actually come along, they integrate with each other. So I'm going to talk about how Cloud Foundry is actually taking Istio and Kubernetes together to provide an industry scale PaaS platform, right? So I'm going to talk about those things as well. So open source, as we know right now, is heavily used in the IT industry. So we're going to talk some of those things here. So if you see this, any cloud platform architecture, right from the hardware to the content layer, you see multiple things. You have the operating system and virtualization, container platforms. So each of these layers, like if you look at hardware, for instance, gone are the days where hardware is treated like a black box. But now the modern hardware has the hardware vendors also are working closely with open source. For instance, you have some of the plugins and adapters that are actually coming up in the open source area, developed by the hardware vendors. So I'm going to talk a little bit more into that as well. And when it comes to operating systems, some of you might have seen Red Hat 8, right? For instance, Red Hat 8 or RHEL 8 has some of the core OS libraries that they have included in the operating system. So these operating systems are becoming more container friendly. Again, this is an open source, multiple open source projects at work. And the other aspect is the virtualization. All of you know that virtualization, like if you want to provision a VM, the virtualization is a key to any cloud platform. So what kind of virtualization technology you use, that will have a bearing on your enterprise scale as well as the container density. So we're going to talk a little bit into that. And then we get into the container runtimes. That's exactly where your applications are running if you're running on a cloud, right? Whether it's a private or public. So the container runtimes, all of them actually originated from the Linux containers. And then you have different variants of that. Like if you look at Cloud Foundry, for instance, you use Garden containers. If you're looking at, like the Kubernetes, it used to manage Docker, and now I think with the Kube 1.11 and beyond, we have standardized on containerd. So in the container runtimes, there are 3 aspects that are coming actually in this. One is the newer lightweight containers, like the Kata containers and the secure containers, and of course the micro VMs like the Firecracker. And then the second one, we're actually changing the way these containers work to bring the agility. And then next layer is orchestration. See, orchestration, if you see Linux used to be a de facto operating system before. But now for the container systems, like Kubernetes has become like kind of a de facto orchestration layer. So when you look at Kubernetes, you get to see two different things. I'm going to talk about that later. But the orchestration layer is becoming like more of a de facto operating system for cloud platforms, because on top of that, you're running all of your various stacks. Let's say you have your applications running in the cloud, and you're running them in the container runtimes, but you need to make sure that you have various platform services like monitoring, tracing, logging, and all that stuff, right? So there are significant open source projects out there like Prometheus, Jaeger, Fluentd. So all of those things, like whether it is Elk Stack or Grafana, right? These are all open source projects. They are providing these required platform services. So some of you might have seen that the industry is actually going towards the microservices in the cloud native world. So when you look at an enterprise application, it's not uncommon to see almost maybe 200 or 300 microservices in one enterprise application. So how are you going to manage them? So that's where the service mesh concept came in. And they are getting more popular, mainly to give you the behavioral insights and operational control of all these microservices within your enterprise application. That's where the service mesh come in. And then the content, whether it is your application or any services, these are becoming, because if you want to consume any of your application or you deploy, now the latest concept that's actually going out is not only you just deploy your application artifacts, but also you need to see whether you can automate the operational aspects. Because if I'm writing an application, I know how to operate that application. So how can you just script that operational experience and make that as an automated operation? That's where the concept of operators came in. Like Red Hat and Google came up with that as part of the extension to Kube. But that's where the content innovation is happening in the open cloud. So now let's take a little bit time on the hardware side. So if you look at hardware, right, it's part of the infrastructure as a service. But what is happening, the modern hardware, whether it is Intel, Power, or Z, or whatever hardware is actually processors, they are getting more optimized towards the cloud platforms, like for containers. Like some of the features, if you look at the persistent volume, persistent memory. One of the key constraints from a resource usage point of view is the memory, right? Because memory, you can get maximum maybe gigabytes, right? You cannot go beyond that, and then you will do the pagination, and then like that's where one single thing for scalability and performance issues. With the latest persistent volume, like this is where the latest innovation in the processors is happening. That will bring your memory to almost terabytes instead of gigabytes. That will significantly alter, it will change a lot of things in your performance, scalability, and even density and the total TCO, right, you operate. For instance, you can exploit some of the hardware on-chip encryption, for instance, because you will be encrypting the traffic, right? So some of our control plane, like where you have the Kube API server, sometimes what happens is 50 to 60% of your CPU that's consumed by the Kube API server is mainly due to the TLS handshakes. So that much you are taking away from the main lane transactions. So think about a hardware processor that is dedicated for these kinds of acceleration, and then offload it to that, and then you have 100% of the CPU left for the main lane transaction, so there is no latency impact, and that is how you scale the control plane. Same concept, like if you use the volume, for instance, the persistent volume I'm talking about, you get into terabytes with DRAM latency, like, okay, a little bit higher than DRAM latency, but 100 times better than a normal SSD. that will open up significant doors into the container density. You can pack more containers into the density, right? Into that pod or cell. And the other area is when you talk about cloud, the noisy neighbor problem is the big one. How do you solve the noisy neighbor problem? Again, for that, there is significant innovation is happening within the hardware vendors, where they come up with some kind of a CPU manager for Kubernetes. So you can actually initialize that on each of the nodes, and that's how you can actually target your workloads to a specific core to eliminate the noisy neighbor problem, so you'll get a consistent throughput. Right? So those are some of the things, and of course the artificial intelligence and the DLAS workloads needs GPUs. So the hardware vendors are actually providing those GPUs with specific adapters and stuff. Right? So I want to just spend some time on the virtualization next. So as I said, there are two different aspects, like when you look at a virtualization, right? I'll just share one of my experiences. Like, we were trying to move from DE architecture to Diego architecture in Cloud Foundry. So we used to have around 200 containers, garden containers in that one cell or VM. Then when we moved from DEA to Diego, all of a sudden our cell was saturated with 30 containers alone. So either you need to increase 7x hardware to support the same kind of volume, or you need to optimize something. So then what we did, we changed the virtualization technology from para-virtualization to the hardware virtualization, HVM. All of a sudden, you saw 200 containers without any problem. So you see 7x improvement just by changing that particular hardware technology. Of course, the HVM may not be the one for every aspect, but those are the kinds of things that you need to change to support the enterprise scale that you're actually looking for. Why the difference? Because when we used PV, it was using almost like 60% higher kernel CPU than HVM. So that's exactly the reason why we're able to pack that many 7x more containers and then just utilize the infrastructure more efficiently. When we look at containers, again, the container runtimes, right, as we standardized on Docker container, so from Docker container to containerd, we basically reduced the additional overhead. And then, as you can see, when we moved from Docker to containerd, we were able to put almost 20% higher parts. So that's another density benefit that you're getting. So this is where you are getting the agility and density benefits. Not only that, but also when you started that 400 of those parts, we have seen significant savings in how fast you can actually start them, from 3 minutes to 11 minutes, almost like 4 times faster startup, right? These kinds of things that innovation is happening within the open source to support the enterprise scale. Now let's talk a little bit about the orchestration, right? As I mentioned, orchestration is becoming the new operating system for the cloud platforms. So what we have found is Kubernetes default scheduler, when we used it for an enterprise scale workload, like a microservices that you have like 6 node cluster, for instance. What we have seen is at certain load, we started seeing a bottleneck, because one of the nodes is becoming saturated, but even though you have enough space, enough room left in the other nodes. That's when last year, I think sometime, I was at KubeCon in Copenhagen, and I was actually talking to one of the SIG leads for the orchestration for the scheduling. And what he suggested was, okay, how about we go to the I was asking for a rescheduler. Like, can we reschedule some of these parts so that it can balance out the cluster? But what I was told was, no, I don't think we can have a rescheduler, but we can have a descheduler. What a descheduler mean is you can actually kill some of those parts in a congested node, and then it'll go back to the Kube API server. Then Kube API server will see, oh, it needs to be scheduled. So it just does that. But again, it uses the same algorithm. So the pod can end up in the same congested node. So you're not really solving the problem. So then I worked with a bunch of our IBM research folks, and we came up with a new algorithm called the safe scheduler algorithm. What we did, we used Kubernetes extensions. We used that. We extended the default scheduler, and also we have used a node annotator to get the information from dynamic information from the cluster. And as part of this, we also supported overcommits so that you can efficiently use the cluster now. So what exactly we did in SSX, we call it as SSX. It's actually open sourced as last month. What we did, we extended the predicates and the priority functions of the default scheduler. So it's not a replacement of default scheduler, but we have extended the default scheduler, so you can specify any part. Okay, I can use this SSX scheduler, right? So we started this at 1.13.5. From that version and beyond, you can actually use this. So the two priority functions that we have provided, like one is the safe overload, the second one is the safe balance. So what exactly they do is actually they take the dynamic information from the cluster's nodes and then add to the static information that you provide from a request, which the default scheduler uses. And it takes those two information in data points, and then it will place the parts more intelligently so that you can have a better balanced cluster. So what it does, the safe overload, right? The first priority function, it orders the nodes based on the calculated risk values, and then the later function, that is the safe balance. What it does is it orders the nodes according to the combined measure of average and the standard deviation. So we calculate the standard deviation, and then that will really look at the available resources, and then that data is taken by this SSX, and then it will do. So combining these two things will give you a trade-off between the average load and the availability and the variability in the load, like the standard deviation I was talking about. So if you look at from a design point of view, so what we are doing is we are collecting the container data dynamically using the node annotator. We'll use either the metric server or the Prometheus, whatever you have for collecting the data. And then we aggregate that data for node, and we annotate that, and then we do the data modeling, and then effective availability will be calculated, and then that's how the feed, you'll have the feed loop there. So you do a static and dynamic monitoring of the cluster, and then you feed that back into the data analyzer, and then that will be how this new SSX scheduler works. How about the oversubscription, right? So to take care of the oversubscription policy, we set two parameters. The first one is the load threshold. The second one is the overload probability, right? And then, as you can see from this chart, right, we explore the mean variance space, and then basically we set a specific operating point. So if you have an operating point that you selected with the low load, then you can afford a higher variability. And if you select a high load, then you can actually have a limited variability. So all those things will be considered, and that results basically in an effective resource usage when you schedule these things. So how are you we have externalized 4 different environment variables to configure this whole scheduler. The first one is the safe utilization, and then like the safe percentile, and these 4 things. When I say safe utilization, what you can set is, okay, if a node in my cluster, if it reaches 90% of the CPU, then you can indicate that I don't want any pod to be placed in that node. Right? So to eliminate any kind of bottleneck. So those kinds of things. And then you can specify the percentile like 30%. Okay, you can say when you are selecting the nodes, ordering the nodes, you say that, okay, anything below 30% risk factor, you select that and then place that as the first one to select when you do a pod placement. And if you want to get more details into what exactly is happening, there is a debug flag. That is the safe printable. Right? So this is actually an open sourced. We did open source it last month from IBM, and I really encourage all of you to just take a look at it, and if you can contribute this further to strengthen this further, to get to the enterprise scale and add more features also. Now let's get into platform scalability, right? Platform services. So once you have your applications running, then let's say you are talking about a production grade or large topology, like you have like 10,000 services or 1,000 or 2,000 node clusters at production level. Then obviously you will be looking at, you will be collecting a lot of data, monitoring data, trace data, and logging data. So how are you going to get these monitoring services? Let's say if you're using Prometheus, how are you get that to scale at that level? That's where we use the operators. So when we were doing this thing, the same thing for an Istio with 10,000 services, we were not able to scale before. Then we used the operators for the Prometheus and Jaeger for tracing. And then we selected a specific knob, because with the operator you can actually specify how you can tune, and then we were able to easily scale that. And what is happening with Prometheus, there are new open source projects like Thanos and others. They are coming up to help you further improve the scalability, and also look at collecting metrics from multiple instances and coordinate those. When we were doing this scalability during the Istio large scale test, we were using the operator, but it is supported by an SSD drive. But as to combine the hardware new features, like as I was telling earlier, now instead of using SSDs, if you start using the persistent volume, which can be actually provisioned as a persistent volume directly, you will see significant reduction. So there is the difference between, from a latency point of view, the difference between a standard SSD and this persistent volume storage is almost 100 times lower latency. So these are the things that will really help you to scale at a much bigger level. So now let me spend a little bit time on the service mesh, right? Because this is I don't know, how many of you have played with service mesh? I think you have a little bit idea about service mesh, or okay, let me explain a little bit on that. Because as I said, this is not uncommon to have a 200 microservice application, right? Enterprise application. So when you are looking at that level, right? And if I'm a developer in banking or healthcare or any other retail, right? So my main focus should be on my domain knowledge, how I can be more competitive in providing a banking or financial services application. But in reality, you spend 40 to 50% of your time in providing for some of the qualities of service like security, traffic management, resiliency, and all that stuff, right? So if somebody can give you enough tools and frameworks that you don't need to spend any of that time, then that 40-50% time can be utilized in further refining and adding some value-added features to your own domain-centric applications. That's exactly what the service meshes are doing. It is increasing the developer velocity. It's improving the developer productivity so that all the things that I was talking about, the quality as a service mesh can provide for you. If you inject the service mesh and get those qualities of service instead of building those things from ground up from your applications. That's why service meshes are actually getting more popular. And not only they're getting popular for enterprise usage, but also within cloud platform, even we ourselves are using service mesh within our own internal components. Let's say we have our UI admin console or any other thing, right? So we consume like the weather APIs that I was talking about. We were using Istio there as well. So let me little bit go detail into the Istio because Istio is one of the more popular service meshes that is out there. So what exactly it does? It gives you connect, secure, control, and observe. These are the 4 different functionalities. When you talk about connect, what it gives you, it will give you an intelligent routing, load balancing, and you can have the A/B testing and canary testing and all that stuff, right? Those features are available to you right out of the bat for this, right? And security, right? It has a component called Citadel. The security, whether you want to handle the service-to-service authentication or certificate management, all those things will be provided. And then control, for instance, if you want to do some kind of policy management or authorization, that's provided by Service Mesh. And if you want observability, like whether it's telemetry, tracing, or even visualization at animation part or distributed tracing, all those functionalities are provided by Istio. So Istio has a control plane and a data plane. The control plane gives you all these features that will control your services which are in the data plane. Right? So from an Istio workgroup perspective, we look at the scalability and performance of both data as well as the control plane, both of them. So what exactly we are doing here, right? So if you look at when we started developing this work group, 2 things we looked at. Okay, if I'm a pilot developer, or if I'm a developer for Mixer or individual components of the service mesh, if I can get the code quality check done right at the day when I drop a code, then you don't need to accumulate and you need to go back and debug those things. That's exactly the process that we wanted to do. So what we did here in this case is we created something called regression control framework. The regression control framework is a framework that you will actually use it on a daily basis to make sure that your code quality is maintained, identifying any issues. Let's say if I'm a pilot developer, if I'm just dropping a code today, right? So that night, let's say tonight, that code will be getting into the build of that day, right? So what we will do is with this, I'll get into the right. All right. You got it. So now you can see all the daily things that you're looking at. So all these builds, once you have those builds, we look at build to build performance and release to release performance on a daily basis. So if I'm looking at a specific problem, what we provide there is we give a comprehensive dashboard. So let me do this one more time here. Trying to get this. So maybe I will just get. Yep, you can see this here, right? So let me get this going. So as you can see here, so I'm the pilot developer. I come every day and just look at, okay, I have dropped the code, how this code is impacting the performance, right? You can clearly see I'll go to a specific 1.2 release, and then I will go and see how, at a very high level, how my code has impacted the performance. If I'm actually suspecting something that it may go wrong, I can quickly just go get this data and then do it. Otherwise, I will get into those 3 specific scenarios, and then one of the scenario you will go and then see whether you have a node specific disk issue, whether you have any kind of a memory issue or the CPU issue, right? All of these things are actually automated. So as a developer, I don't need to go to any performance engineering guy to get me the data, because everything is there available on istio.io right there. So I'll go and take a look at it. So let's say I need a little bit more data because I want to go a little bit deep into a specific thing. Then that's where we provide the integrated Grafana dashboards. So I'll go and just click on the Grafana dashboard for that particular build. And then all of a sudden you will see at least like tens of different dashboards. So you can see the Grafana dashboard here. You have the Istio dashboards, pod metrics, and worker metrics. So when you go to the Istio dashboard there, and you will see at least like 4 or 5 different things. So you have a pilot or a mixer, and let's go to the performance dashboard. So this dashboard is also useful for sizing and capacity planning also, right? How much resources you need, how many VCPs you need to do 1,000 RPS, right? So this is all automated and readily available for most of the development teams. And you can actually look at what are the different nodes, how what vCPU, how many RPS, and all that stuff. More details about the application that we have used to generate this. And then you can actually look into individual areas, right? If you're based on what area you're actually developing. Right? So once you get this data, and then you can actually pinpoint that, oh, yesterday's code I dropped has actually impacted negatively the mixer part, right? Even though I'm not intending to do that, but it has the side effects of that. So as we have introduced this kind of regression patrol framework, we have identified so many bugs on a daily basis that code quality has improved significantly. So these are the process changes that we're actually doing, and you can also go to individual areas like the different like maybe a disk or memory or like a specific area in how many Go routines that your specific code is using. All that data you can actually get that, right? So let me just go back. Okay. All right. So this is actually a process change that we introduced here, right? Apart from that, there are multiple design and architecture changes that we have introduced. One of them, I'll give just a couple of examples, right? How it has impacted. Like for instance, if you're injecting a sidecar, your service is there and a sidecar sitting, both the containers are sitting in the same pod, right? What we have seen is the traffic has to go via the kernel from service to the sidecar. That is adding significant network bandwidth, like almost 60%, you are using 60% additional network bandwidth because they both are sitting in the same pod, and you can actually directly go using the this just user space directly, right? So you can do that with eBPF, right? Those are the kinds of things that we're optimizing so that you can get the scale. And then another aspect that I want to talk about is the pilot, for instance, right? Because pilot controls the traffic, how the sidecars all are getting the configuration, everything, right? So what we are trying to do is we are trying to distribute the traffic between pilot and the sidecars in a uniform way using the gRPC libraries to control more dynamically these things, right? So some of those, and then Knative, some of you may be familiar with the serverless framework. Knative, under the covers, it uses Istio. So what we do is we look into, okay, Knative, one of the main thing is how quickly you can start your containers, how quickly you can collapse, right? So those kinds of agility stuff is really important for Knative. But Istio doesn't, like for a normal application, here you can see around, startup time of 200 milliseconds is not much. But for Knative, it is really, really too much for Knative serverless. So what we are doing to do that, to optimize Knative, we are trying to use some of the optimizations to significantly reduce this cold start from 200 milliseconds to 0 millisecond. And another aspect is for Knative is required is like kind of the init container that we have in Istio. That is also actually adding significant cold startup time too. So that's another area we're optimizing. So as you can see, when two different open source projects are working together, right? So we will make sure that when they are integrated, we get the enterprise scale requirements met, right? So that is just an example. And the content, right? As I mentioned about the content, operators are becoming the next generation of how you consume the content, whether it is your enterprise application or whether it is like a stateful services, right, or messaging or middleware or anything. So the operators with the Go controllers, because basically what we do is we script the operational experience using the Go controller and then make that available as an operator that you can actually just configure later on, just only minor things for your specific situation. So these operators, if you go to operatorhub.io, there are already a lot of people who are actually putting operators in their individual middleware vendors and the service vendors, everybody. And now next one is the how some of these frameworks, open source frameworks, are actually working together to provide an enterprise scale solution. I'll give you an example of Cloud Foundry, right? So Cloud Foundry, when it started, of course, it's a true PaaS platform with opinionated view there. So it has its own application developer experience, and then it has its own scheduling, you have a Diego scheduler. So you do a CF push, it will push an application, it will deploy an application, and then it will schedule it on a specific Diego cells, right? At one point last year, we decided that, okay, why do you want to use a Diego scheduler? Because industry is going after Kube scheduler, because Kube is becoming, like a de facto scheduling, because full community is behind it. Then we started a project called Project Irene to replace the Cloud Foundry's Diego scheduler with the Kubernetes Kube scheduler. That is solving one problem so that you don't need to learn a separate scheduling, but still you keep the value proposition from Cloud Foundry, like the CF push with the application developer experience, that you still have that. And then we looked at other areas. If you look at Cloud Foundry, routing is provided by GoRouter. If you look at Istio, routing, and as I showed the dynamic routing and all the policies, right? That is provided by Envoy proxy. So then we decided, okay, can we replace the GoRouter with an Envoy proxy so that you don't need to have a separate thing, because all the innovations that are coming in Istio, you can take them here. And then for security, you take UAA in Cloud Foundry. And as we have seen in Istio has its own security provider, and Citadel provides so many of security qualities of service. Then we thought, okay, can we replace some of this UAA stuff with Istio? As you can see now, Cloud Foundry is going to be working closely with Kubernetes as well as the Istio. So all these three frameworks are working together. So right now what we are looking at is when these three frameworks working together to provide a PaaS platform to enterprise customers, whether you have the right integration scale, right? It's there, right? Those are the kinds of things that we're actually looking at this point. If you want to get a little bit more information about Project Irene, you can actually go and look at that, and also the integration between the Cloud Foundry and Istio, more architecture details like you can see there. Right? So to sum it up, like we went through so many of these things, right? So first and foremost, we have open source cloud technologies are vetted for enterprise scale. You have seen some of these examples. And the new kube scheduler for a better enterprise scale, right? We came up with that, and it's an open source. I encourage you to go take a look at it, and please, you're more than welcome to contribute to that also. And then Istio performance work group is actually introduced a regression patrol framework to control the code quality. And this can be used by any other community also, like just so that you will not have accumulated issues later on, like on a daily basis you can control. And hardware exploitation is the next best thing because of the hardware as it's evolving for cloud. So the TCO for cloud, if you want to control, you have to exploit that. Operating systems are becoming more container friendly. And the operators are the next best thing that is actually happened to the content for cloud, because now you're actually getting the content, and also you're getting the operational experience scripted and giving you a nice automated way, right? And of course, you have to choose the right virtualization. When you provision a next VM, make sure that you are selecting the right virtualization, as you have seen, like 7x difference in there. So as I mentioned, open source is heavily used in IT at this point, but we are just scratching the surface. Every industry can benefit from open source. It may be banking, it may be retail, it may be government, right? Every industry, healthcare, right? So I strongly believe that open source is going to get into these different industries also, and then it's going to make life easier for everybody, because you can get a better tools and better mechanisms and regulations and stuff too. Right? I think with that I conclude. So any questions? So are you talking about the CPU algorithms? So CPU sharing algorithms?
Yeah, to take advantage of CPUs on the network cards and whatever to handle HTTPS, just to offload some of the work.
Yes, yeah. I think the question is how does the new CPU algorithms are actually being exploited to take care of different workloads, whether it's HTTP or TCP, right? Right. That's the question. So I think two things are happening. One is to exploit. The second one is to eliminate the noisy neighbor, so that what is happening is you can use the CPU manager that I showed. There are some CPU manager drivers that are available. You can deploy them on individual nodes, and actually that you can pin your specific workload to a core, right? That will eliminate this CPU noisy neighbor problem. But the other area that we are looking at is how can you get the CPU shares vetted in a congested environment. Let's say you have 4 or 5 different contenders for the CPU, and then you have requests and limits specified, right? So we are tweaking some of the CPU sharing algorithms to give the CPU sharing in an equitable fashion, so that there is one hungry application won't take everything. Right? So those are, yes, we are working on multiple work groups there. Any more questions? Okay, thank you.